Doesn't really matter. That could be up or down. I think I'd put them all down just to be, just so you wouldn't be confused on that. The little arrow, who knows whether it represents +1/2 or -1/2. That's a quantum number, not an arrow. But that was the same in all of them, just so it wouldn't be too confusing. M sub L, the third number, M sub L can be -1, 0, or 1 if L is 1. And there's no way to tell which is which. So any of those would have been okay either. So basically, the first two quantum numbers, N and L, define that thing there. And M sub S is +1/2 or -1/2. And M sub L is one of the values of M sub L. But there's no way to tell from there. All of them are legitimate. All of them are fair enough. Could be any one of them. So there were a couple correct answers, is the short answer to that. Pop quiz, that brings up a good point. So as you know, we tried to do the class. Oh, just text her and say there's, yeah, sorry. Maggie, hyper efficiently, I was holding some in my hand. Maggie's already over trying to scan them. So pop quiz, why do we give you the pop quiz? Well, two things. One, we're hoping that you go back and review your exam after you see it, and you come in and you take another shot at it, and gives you a chance to improve your score. If you're nervous, you can just put in the same exact score that you got on the same way you answered it on the midterm. That's fine too, nothing changes. But there's another reason. We're trying to do the class all online, and many of you benefit from that. You don't have to come here. You don't have to come to campus at all if you don't want to, even for the exams. And that makes it convenient and easy in many respects. It makes it an online class if you want it to be. Technically, many departments on campus, including the chemistry department, don't want to have online classes. Well, it's a split among the faculty. Some people say, yeah, go for it. Some people say, don't. I'm one of the people that say, yeah, let's get as many people taking Chem 1 as possible. Make it easy. The room only holds 500, but 1,000 could take it. I mean, they don't all have to be in the room on any given day. So why not make it easier to roll in Chem 1? Many of you probably know if you try to take it in the fall, sometimes you're kicked out. There's not a space, there's not a seat. Why should you be kicked out? Because there's not a seat. So we'd like to have it online. Can we give you the exams online? That's another thing people complain about. And the question is it fair? If we give you an online exam, we know there are resources out there you can use. The question is, do you use them? And the question that the way I like to phrase the question is, if I give you an assessment online and I'm not watching you, is that still an indication of how well you've learned it or not? Or is it an indication of how well you can use Google? I don't know. So, but that's a fundamental question, and it just got worse, as you know, because ChatGTP just came out. You guys are the first people to take exams at Cal after the advent of ChatGTP. So we wanted to know, is it in the era of ChatGTP, can you give online exams and be fair? But there's a lot of ways you can, work on an online exam that you wouldn't work elsewhere. You could collaborate. There could be a bunch of people in the room. You could, do all manner of things. The question is, regardless of what you're doing, what your resources are, can we write assessments that still tell us about what you understand? So we tried to do that. As you know, the assessments are, they're pretty complicated in a way, and they're complicated for that reason. We don't want you to be able to, we want to make it make sense for you just to learn it, because it's really hard to Google it. You might as well just learn it, because you're not going to be able to use ChatGTP or Google it when you get there. Other resources, You know, you could be 5 of you in the same room, but we try to have 5 different versions of the exam. So, if 5 of you are going to collaborate, at least you have to do 5. Each one of you still has to do a question, more or less. You still got to do it. So we hope we can get around these things, but there's just a lot of skepticism that it doesn't work. So I need a favor from you guys. I want you to demonstrate that it does work. I want you to save online education at Cal for everyone, for the benefit of all. But I have to ask you a big favor. The way that my colleagues in the department have said that I can show them that the online assessments are a good indication of what you actually know is to give you the final in person. If you take the final in person and you do the same that you did, or better, if you do the same as you've done all semester long, then yeah, we've apparently taught you something. And it didn't matter that you were doing 3 of the exams online. You can show us on one exam that, yeah, you get it. You can respond to those questions. So we told you the final is going to be online. I'm going to ask you, please, to take it in person. I'm going to I'm asking you, but I'm going to give it to you in person. I'm sorry. The exam will be in person, the final exam. It's a big ask. We know that we haven't told you till now, so maybe you have travel plans. We have, it's going to be the same time that we have it on the syllabus. When do we have it on the syllabus? 6 to 9 on Thursday, a week from today. Same time, you're just going to have to come to campus to do it. And I know some of you, may have planned to have left for home and do the exam from home because it was online, which is what we want you to do. But we have to prove that it's fair for you to do that. So by coming in, you're going to help the next group prove that it's okay for the next group to fly home and do it from home. So come in, and that's, of course, why you probably guessed, why did we do bubble sheets today? We've never done the bubble sheets, so we figured we better practice once before we do it in person. But we understand it's short notice. We understand some of you have already left and are at home. There's people on the East Coast. They said, okay, I'm going home. We're not going to make those people fly back. So there will be 1 or 2 of you who, but that's actually okay. 1 or 2 of you to show, they got about the same, scores, whether they were online or in person. But everybody who's here should take it online. If you have a problem with that time, or there's something that you need accommodation, we can move the time a little bit and still give it to you in person. We have some flexibility. So to email Zev and say, I have a conflict with that. Can I take the exam at a different time? So do that, get to him by Tuesday. We'll give you some time to arrange things. But otherwise, we'll be in which way do I point? Over there in Evans, 100 Evans, I think, or 1 Evans. We'll post the room, obviously, at 6 p.m. on Thursday. Okay, sorry, big shock. But I'm actually excited because overall, I don't think you guys are using outside resources. We asked you not to, and we have ways where we can tell that there is some fishy business going on. And I'll tell you a secret. We can kind of tell if you use ChatGPT, believe it or not. So some of you do. We'd rather you didn't, but by and large, the numbers are very small, I think. And I think we asked you guys to be honest, and I think 98% of you are being very honest and taking it. And I think you're going to show me that by doing well on the final. So the final will have questions that look very similar from the previous material, and you'll be able to say, yes, I get that. I can answer it in person. Well, we're on the subject. It goes so fast near the end. What I usually do is I do emphasize the final questions on this material, starting next week. There are actually fewer questions on that. We try to ask the most obvious, straightforward questions on the last week of material because you've just seen it 2 days ago and you have to take an exam. So most of the stuff will be midterms 1, 2, and 3. And then we'll have, there'll be something like 60 questions and, only 10 of them or so will be on the newer material. So we understand it's difficult to do this in the summer. No, it's Thursday? It's on Friday. Oh, 6 to 9 on Friday. Oh, I'm sorry. Sure. Is that a bad time? That is a bad time for some people, right? I thought we got the room on Thursday.
Well, it just says on the...
When's the room?
It says Friday on the syllabus.
But we have the room on Thursday. Do we have the room on Thursday?
For DSP students, yes. For the rest of the class, you book through it.
We have...
And I think you have it on Thursday.
I think the room is on Thursday. Yeah, sorry, the day is also changed. What? I'm sorry. Here's the thing. We know that you have to go home. So we discussed it, and maybe okay, so I'm just not remembering how we discussed it. We discussed it in the staff, and we said, oh, if we're going to do it in person, you better do it Thursday because people have plans to leave on Friday. That's why we did that. So we're checking. We'll check the emails and see when we have the room. Thursday, 6 to 9 is when we have the room. So sorry, that's another big. Well, actually, if we had it Friday, it would have been a bigger problem because many of you had. We heard from half a dozen people that said, "I'm leaving and I'm going to take it from home," because you could. Those people can still take it because it's going to be Thursday at 6 p.m. So you're doing me, you're doing all of Cal a big favor by taking it Thursday at 6 p.m. Thank you again. We will, like I said, we'll take into consideration that the exam is the last day of class, and we will have, the last day of class will be totally review, and the material from Monday and Tuesday and Wednesday next week will be limited, and we'll try to make it obvious from the homework what questions will be on the exam. Hint. Okay? All right. Sorry for the mild confusion there and the shock, I know. But I'm counting on you guys. I'm counting on you guys to come through and demonstrate that you have learned chemistry to the whole campus and to the world and to our department and everybody who questions whether this works. Okay, so we've been talking about intermolecular forces, and we ranked them by strength, and the important thing is we said it depends on the structure a little bit. Well, mostly depends on the structure. So things that are large and polarizable. So they're not polar to start with, but they're polarizable. So the electron cloud is susceptible to moving around and giving you a transient dipole. That's where the perfectly symmetric or stuff that does not have a dipole, we know most particles condense into a liquid. So if there are no other major forces involved, it's this transient induced force, often called dispersion or van der Waals interaction. You sometimes see that, but it's just the wobbly electron cloud of the larger and loosely held electrons that causes a instantaneous, an induced dipole that causes condensation. And that goes with the size of the particles. So you can see the bigger particles, they have higher boiling points because they have more intermolecular forces. But when these important dipole forces, and especially the hydrogen bonding forces, are an effect, you can see here when you go to the less polarizable molecule, this methane molecule, it's kind of the same series here, but once you have a potential for a dipole and a large difference in electronegativity, you start getting dipole effects and then the very strong hydrogen bonding effects. If you have a hydrogen bonded to a very electronegative nucleus, you have this, and this is thousands of times stronger than this, and only about 10 times less than an actual covalent bond. So this is just an order of magnitude less than an actual covalent bond, and it gives you these very high, you could say anomalously high boiling points, and you should be able to correlate boiling point with the structure of the molecule now. You could not do that when we took midterm 3 or midterm 2, but now you can correlate boiling points with the structure of the molecule. And here we can do it. I don't think anybody will be very challenged by this, so we'll talk through this together. Here are 3 molecules, which has the highest boiling point, and you have 3 molecules with the potential for hydrogen bonding, because they have hydrogen bonded to a central atom here. The question is, which is the more electronegative and which would cause the greatest dipole? And we know oxygen is the more electronegative of nitrogen and sulfur, so this dipole is bigger. So you have a stronger hydrogen bonding interaction potentially here. These guys have the dipole interaction, so they do have a higher boiling point because they have the permanent dipole, but this one is so strong, you also get into the regime of strong hydrogen bonding. You'd have weaker hydrogen bonding here and very weak there. So highest boiling point is water in this case. It just, you have to get hotter to pull them apart. Higher, we know hotter means higher temperature, means more kinetic energy, and that kinetic energy has to overcome the potential energy that's holding you in this well. You've got potential energy holding you together in this well. You have to give the molecules enough kinetic energy to get out of that well and break those intermolecular potential interactions. So let's go back briefly and look at the entropy of the situation. Just to remind you, we talked about the entropy of vaporization, and we related it to the enthalpy of vaporization. So now we know this depends on the structure of the molecule and the boiling points. So what we find, though, that the entropy is the enthalpy of vaporization over the boiling point. So the entropy of vaporization can be taken by this reversible process. We know it's reversible because we're at the boiling point. So we're at equilibrium. We're at the case where this really is a reversible reaction. Take the enthalpy at that point over the boiling point, and that is the entropy. But that was thermodynamic. It wasn't very intuitive, but we also have this intuitive view. When you have the this statistical view, the liquid going to the gas, that's a large increase in microstates. Not very many microstates in the liquid, lots of microstates in the gas, and entropy does not care about the energetics. It's just statistical. Even though you can calculate it, you can get a calculation of the entropy from a thermodynamic property, you have to do it under the reversible processes. You have to be very specific. So by and large, entropy does not care whether it's a water molecule or a H2S or an NH. Those all had different boiling points, but the same entropy of vaporization about. And here you can do it. You can plot the entropy of vaporization versus the boiling point for many different compounds. And you see, this is they all have the same ratio. They're all the same, they all fall on this line. This ratio is the same for vaporizations of many different molecules. So our understanding of microstates and the fact that there are many microstates here and a few microstates here, and it doesn't matter the nature of the particle. All you're saying is there's lots of ways to arrange them here, and there's not as many ways to arrange them there. That's all that matters for the statistical understanding of entropy, and we see that borne out in this plot. Interestingly, though, there are outliers. So water, for instance, 40 kilojoules per mole at 100. Whoops. C. Don't I plot that somewhere? Whoop. That's off the line. Water doesn't follow that trend. So we say, why doesn't it follow that trend? Why is this entropy so different? Well, it is coming from the fact that we know it has this hydrogen bonding interaction. The hydrogen bonding interaction is giving you an enthalpic thing, but it must also be giving you some kind of entropic contribution. There must be something different about either gaseous water or liquid water that makes the entropy different too. And what is that? Well, let's talk about it. Let's talk about it first in kind of review. We kind of were hinting at this on the previous midterm, but we gave you molecules where you could not see the structure. And we did that intentionally because we didn't want you to think about the structure. We hadn't talked about how the dipoles and the interaction could influence this. But you can see these went kind of by their size, their polarizability. This one has the larger size, more polar, more transient interactions, and a higher boiling point. And we looked at those two, but we said to ourselves, well, if we want to talk about the entropy of vaporization, well, if we do the entropy of vaporization at 350 degrees, so let's cap these, put a cap on all of them. The entropy of vaporization at 350 degrees, here are the equilibrium constants at 350 degrees. So this one, well, 350 degrees is its boiling point. So at its boiling point, what is that partial pressure, if that's the boiling point? What's the partial pressure of the carbon tetrachloride? 1 atmosphere. That's the definition of boiling point. How do you get to the boiling point? You get to 1 atmosphere of vapor pressure. So this one, we didn't have to tell you, at 350 degrees is 1. You're supposed to know that definition. The definition of boiling is we get to 1 atmosphere of pressure. At 350 degrees, what's the partial pressure of this C4H10? 1/4 of an atmosphere, right? This, what we write is the condensed phase going to the gas phase. K for that reaction is the pressure of C3H8O gas. The liquid doesn't appear in the equilibrium constant, does it? So the equilibrium constant is the partial pressure of the gas. So this one has 1/4 of that. This one, oops, did I do the right one? Yeah, 10. And then this one has almost a little over half an atmosphere of gas at 350 degrees because they are not boiling. They're at equilibrium, but they're not boiling. This one is equilibrium and boiling because it's at its boiling point. Okay, so now let's say we want to compare the entropy of vaporization now of those at 350 degrees. So we'd have to say, well, how many microstates are there in the gas and how many microstates are there in the liquid? That's how we would find delta S, microstates in the gas, microstates in the liquid. But there's a little bit of a problem there, isn't there? There's more gas in this one. So we really can't compare this one to this one because this one's going to have more microstates just because there's more gas. So I can't compare this one to this one to this one at 350 degrees. So what I'd like is some way to compare things all the time that we could all agree on, some set of conditions. Yeah, why don't I put them all so they all are 1 atmosphere? It's not equilibrium, but I have to do it. I have to put an atmosphere there and an atmosphere there if I'm going to compare the entropy of vaporization at 350 degrees for all of them. And I'm going to put delta S standard state. Now it's fair for me to compare because they all have the same number of gas particles above the liquid. Do you see why we have the standard state? You can't just compare unless you say, let's put everybody in the same state, and then it's fair to compare. And it's obvious for the entropy. It's not so obvious maybe for the enthalpy and all that, but you see it obviously. It's not fair to compare unless there's the same number of gas particles in each one of those. Otherwise, there would just be different entropies. So if you get to the standard state, then yes, it doesn't really matter what the particles is. A mole of gas has about the same entropy regardless of what that gas is, and a mole of liquid has a very similar entropy regardless of what that liquid is. Similar enough that standard state enthalpies of vaporization are about the same for most compounds. Is that a lovely place to come to? We keep coming back to standard state, and you know it's going to be on the exam. We're going to ask you, what is the standard state? Now you can see, of course, I have to be at standard state, or it's not fair to compare things. And that's why we have the standard state. We just want to be fair in our comparisons. So why is water off scale? Well, water, it turns out, even in the liquid state, has some order. The hydrogen bonding is so strong in water that the liquid water molecules are organized around this hydrogen bonding. So the liquid water molecules don't have as many microstates because they get constrained. This one relative to that one, relative to that one, relative to that one. There's limited ways they can be constrained because of that strong hydrogen bonding. So the entropy of liquid water is lower. So we said, well, maybe we'll do it. I don't think we have a slide for this one. We said that standard state entropy, gas, liquid, delta S standard, we said that's about the same for most compounds because a mole of gas has a certain number of microstates, a mole of liquid entropy per mole is about the same across many liquids. So this gap is about the same for most compounds. Water is not. Water had this bigger entropy of vaporization. But now we can see why. Because liquid water, gaseous water, about the same. Once you get into the gas phase, it acts like any other gas, really. You separate the particles. But here, if this is most compounds, their relative entropy, where do I have to put water? It has fewer accessible microstates because it's constrained. So is that a higher entropy or a lower? Lower. So water is down here. And so it has, yes, water has that higher entropy of vaporization, not because the gas is any different, but because the liquid is ordered, is constrained, fewer microstates in the liquid due to hydrogen bonding. And like I said, this is one of the most important things that you should take home if you're going to go into molecular biology. It's one of the most important forces in your cells. It dominates what can happen in the cell. Okay, that's the nuts and bolts stuff, so that we'll do later. Where do we go from there? Looks like we go here. So let's continue to talk about the equilibria of liquids, gases, solids. So we're going to go back to equilibria, and this is a heterogeneous equilibria we're talking about. It's a liquid and a gas. So those are two different phases. So let's talk about those phases now in more detail. Let's just take a different gas and dissolve it in water. So not the water particles. We know the water particles are there, but what if you dissolve carbon dioxide in gas, in liquid water? It does. And we'll go through this relatively quickly because it's just a review of equilibria. What if the phases are different? Well, you know you can still write the equilibrium quotient, and I will reinforce, you can prepare this in any possible number. This is just a ratio of whatever the products happen to be and whatever the reactants happen to be. It's not at equilibrium. It's not even related to the equilibrium. You can relate it to the equilibrium constant if you want, but you can put any two numbers in there. You can put any concentration here and any partial pressure there. Q is just a ratio. You are allowed to compare it to equilibrium. Whatever Q you prepare, you can compare it and say, where will I go from this thing that I prepared? But you can prepare any number. At equilibrium, it does become a constant. That ratio becomes a constant. So you could write it like this. Here I've just solved the equation for the concentration. I just multiplied the partial pressure up. So the concentration of the gas dissolved is the equilibrium constant times the partial pressure of the gas. And this has some intuitive sense. If you have a high concentration of gas dissolved, that would lead to a high partial pressure of the gas above it, directly proportional. If you want to make the gas dissolve, then increase the pressure. And you know, if you've ever seen carbonation, how do you get something carbonated? You put a high partial pressure of carbon dioxide, and you force the carbon dioxide to dissolve in the gas. So you know, when you open a soda, you can hear that partial pressure of carbon dioxide decreasing, can't you? And what happens immediately as that partial pressure decreases? Well, if this partial pressure decreases, then the solubility, the amount of the concentration of the carbon dioxide goes down. And the carbon dioxide starts to come out of the liquid and back into the gas phase, and you can see it bubbling in the liquid phase and going into the gas phase. So Karen can demonstrate that for us dramatically. Why don't you come on out, Karen, and we'll look at that. Here are just some various equilibrium constants for those. This is kind of telling you the solubility, isn't it? It's telling you for a given partial pressure, if this is big, then you get a lot of dissolved gas. So helium isn't very soluble. You have to put a very high partial pressure to get helium to dissolve. This number is small. Carbon dioxide's pretty soluble by comparison, hundreds of times more soluble in water. For the same partial pressure, you can see you have almost 100 times, if the partial pressure of carbon dioxide or helium is 1, you would have almost 100 times more carbon dioxide in the liquid than helium in the liquid. And there's a crazy one. 10,000 is the dissolving ammonia gas in water. So a tiny partial pressure of ammonia gas still leads to a high concentration. This is very soluble. It wants to dissolve. What does large K mean? It means the free energy is very big and negative. It's going to go towards that dissolved state if that's how we write our equilibrium constant. And you can see, oh, look at this one. This K is less than 1. What does that mean? Yeah, that one's not soluble, and it's not even spontaneous for it to dissolve. Delta G is negative for that one, the standard state, if you put 1 atmosphere. Remember, we compare them all at 1 atmosphere. Why? Because that's fair. One atmosphere of this, if you put 1 atmosphere, it would want to go and decrease to a quarter of atmosphere. This would want to dissolve strongly and go to a higher concentration. So this would want to go to low concentration. This would want to go to high concentration. You would start out with 1 molar gas dissolved and 1 molar of the, or 1 atmosphere of the gas above it, and see where it goes from there. And the size of the equilibrium constant tells you that. So if we could have a shot of this, what Karen has here is somehow you've trapped ammonia gas in here. So there's ammonia gas in here, and there's some liquid water down here. We've got a colorizer in it, so you can tell, pH indicator actually. So that water is connected by this hose, and otherwise that's sealed. So the pressure in here will determine the level here. So right now there's an atmosphere-ish of pressure of ammonia in here, and you know that because there's an atmosphere of pressure on this gap, on this liquid. If you made lower pressure in here, then this higher pressure would push down and force that up into the flask. So if this goes to lower pressure, we would expect this level to decrease because it's going to be essentially forced up there by the atmosphere. If it went to higher pressure, then gas would bubble out of here down there. So what Karen's allowed to do here is she's got ammonia gas, and she's going to put a few drops of water in there with that little syringe. And just a few drops of water will dissolve a lot of ammonia gas. So the pressure is going to dramatically decrease. We're going to take those particles out of the gas phase into the liquid, dissolve it into the liquid. The pressure is going to dramatically drop in there. And what do we expect? We expect the atmosphere to shove that orange liquid into that beaker. So go ahead, Karen, and do that. Let's get a good shot of it. And as I said, go ahead. Let's see the big shot. Okay, there it goes, fountaining up. Can we zoom out? Oh, nice camera work. Brilliant, guys. Thank you. You can see a little leaking. Oh, no. Oh, poop. What's happening here is this is leaking. You can see it's leaking right around the edge there. Can we? It's moved a little, but we have kind of a leak here. And actually, it's drawing air into this. It's drawing air. Oh, this might be a crack in this tube because it's drawing air. There's a lot of air in there. Karen, I'll diagnose that. All you saw was just it's moving up there, but slowly, because there's a leak, and it's drawing air from the atmosphere in there too. So it's not as big an effect. We'll get that diagnosed. It's worth, Karen, it's worth trying to do if you have enough ammonia. It's worth trying to figure out. We'll do it tomorrow because it's dramatic. But I want to tell you this gigantic K means I favor that dissolved liquid very strongly. I favor the dissolved liquid the dissolved gas very strongly, and that means way downhill in free energy to get to the dissolved gas. And you know free energy release is the amount of work the system can do. It's the amount of energy that can be used for work. And it's giant in this reaction. And when this goes, and it is going, it's going very slowly, but this is 3 liters of water. 3 liters of water, you know, weighs nearly 10 pounds, probably 7-ish pounds, a couple kilograms of water here. So this reaction has enough free energy release to lift a couple of kilograms of water a foot off the ground. So you can see the actual release of free energy can actually do that work that we said it can do. So a lot of brilliant equilibrium chemistry comes into play there. The size of this equilibrium constant strongly favoring dissolving the gas into the liquid. That giant free energy, many kilojoules per mole of dissolved gas, gives you enough joules to literally lift water off the ground. Brilliant connection. So let's just do this one. Together, the teaching assistants can go talk about it. Here you have a solution, equal concentrations of helium and nitrogen dissolved. So if equal concentrations are dissolved, what does that say about the partial pressures above the liquid? I'll see if I can get you some hints for that. Go ahead and talk about that one among yourselves. And teaching assistants can help you talk about that. Okay, did I turn on the thing so you can actually vote? Go ahead and enter your thoughts on that. You had some time to discuss it. We'll see what you're thinking. So, survey says, another game show aspect to Chem 1. Many of you were thinking that the partial pressure of helium should be higher. So we know this equilibrium constant is lower than that equilibrium constant. What does that tell you? That helium is the less soluble gas. You have to have a higher partial pressure of helium to get the same concentration of that you would of nitrogen. Nitrogen has the bigger K, so a smaller partial pressure of nitrogen would give you the same concentration as helium. So you could look at it more soluble. Another way to look at it, say you prepared them in the standard state. So you put 1 atmosphere of gas there and 1 molar of each of them. I should write that down because it's getting complicated now. So let's say you put 1 atmosphere of helium and it's not neon, it's nitrogen gas, and you put 1 molar of concentration of both of them. That would be the standard state. Everything 1 molar or 1 atmosphere. And you would say, where would it go from there? Well, the K standard state, the K for helium is less than 1. So from the standard state, it goes back towards the dissolved, and its pressure would drop. The K for the nitrogen is slightly bigger, so it's spontaneous to go in the other direction, and its partial pressure would go up a bit. So they would go in the spontaneous direction from the standard state is exactly what K tells you. Where do I go from the standard state? And the result would be a little lower, or wait a minute. Did I do that wrong? Oh. That K is negative. Oh, okay. Sorry. Let's write out what K is. It's the HE aqueous going to HE gas. And we write the K for that is the, well, it's not how it worked. I have reversed it. It's the, I mean, it has to be this for the explanation to be right. Gas going to aqueous. This concentration, the equilibrium we're talking about is, oh, come on. For goodness sakes, stop. The equilibrium we're talking about is helium gas going to dissolved helium, helium aqueous. So if we write that K, that Q, that equilibrium expression at equilibrium, it's products over reactants, it's the helium aqueous concentration over the pressure of the helium gas. So we know that K is less than 1. If we start at 1 atmosphere and 1 atmosphere, it goes back towards the gas phase, and the helium gas goes up a little in pressure, and the nitrogen gas goes a little down in pressure. And we get the same result. Sorry about that. You can see even a so-called professional can do things backwards occasionally. You all have done this one. We'll talk through this together. On a warm day, a can of carbonated beverage expands a little bit. So you take it out of the fridge and you see the pressure increasing inside. So increasing temperature, again, we know increasing temperatures affect K. K is a function of temperature. So now we're going to see the solubility, or the amount of carbon dioxide dissolved, is a function of temperature. And if it's going up, the partial pressure is going up. We know that, we'll write it again. The equilibrium expression is CO2 gas going to CO2 aqueous. And what we see as the temperature goes up is we see this partial pressure increasing. So if that partial pressure is increasing, we have the reaction shifting back towards the reactants. Shifting back towards the reactants tells us about whether that's an endothermic or exothermic reaction. We've seen that many times now. That's a review of the stuff we have learned from the beginning. There it is. If I have this reaction going back in reverse as I increase the temperature, we say one way to rationalize that, or maybe it's on the animation, doesn't look like it is. One way to rationalize that is that heat is a product, and as the temperature increases, that goes back in that direction, increasing the partial pressure of the gas, and that is what we're finding. The heat is released. It's an exothermic chemical reaction, or exothermic process. There's our reminder. K decreases with temperature for the exothermic reactions. Okay, good reminder for what you'll do next Thursday. Everybody can respond to this one. Everybody happy with that? Okay. So we can do the same thing with solids and liquids. So solids dissolving in liquids. What we have here is a expression, the solid dissolving and forming the ions in solution. So this aqueous means I'm dissolved in solution. I should be able to get a concentration. Remember those brackets are concentration in moles per liter. I can write Q at any concentrations. I could compare it to the K, but you know from your rules of writing equilibrium constants that the solid, the pure solid, doesn't appear in the equilibrium expression. So it's just an equilibrium quotient. I'm sorry, it's just an equilibrium product as opposed to an equilibrium quotient. It's just the product of these two has no denominator because the solids don't appear. And we can write those. Sometimes we give, it's just a K, but sometimes we put little subscripts on our Ks. Doesn't really matter. It has all the same properties of an equilibrium constant. That stands for solubility product because it's a product and it determines the solubility. Why does it determine the solubility? Because the bigger this number, the more it lies towards products. So the bigger the K, the more dissolves, the more soluble the compound is. So solubility is rated by these solubility product constants, and you can see barium sulfide not soluble at all. That's a ridiculously small K. The product of that concentration and that concentration at equilibrium has to be 10 to the minus 10. So they're both very small numbers, or at least one of them is ginormously small number. So not very much of this dissolves. It's a sparingly soluble. This is going in this direction is not spontaneous at all. It's horrible going in that direction. If you did standard state and you put 1 molar there and 1 molar there, it has to go from 1 molar, 1 times 1, it has to go from 1 all the way down to 10 to the minus 10. So it's going to go flying back and make the solid and reduce those concentrations till their product is 10 to the minus 10. Okay? All that stuff should be gelling in your mind here near the end of the semester. So if you just put a little solid in, those concentrations will be equal. So you say, well, if the concentrations are equal, then the product of them is 10 to the minus 10, so each of them would be about 10 to the minus 5th molar. And indeed, almost undetectable concentrations of barium and sulfate in there. Almost undetectable. We're just going to skip that one altogether. Oops, no, we're not. I'm going to talk through it because it brings up a point. I want to make, I've got some barium sulfate and I want to make it dissolve. Which one of these should I add to make it dissolve? So let's just talk through that together. There's what I want to make it dissolve. This barium chloride is very soluble. The K for this is gigantic. It goes way towards barium and chloride. So adding a little barium chloride is essentially like, do I write down the K for this? I don't write down the K. You're just going to have to trust me that it's, does it show up in the animation? It doesn't. Trust me. And this is how it would work on an exam. Basically, if I give you a KSP, then it's insoluble. If I don't, it's soluble. You can assume it. You can assume the things that you don't get a KSP for dissolve all the way. Like table salt. You put table salt in, NaCl, all of it dissolves. Barium chloride, similar salt, all dissolves. So what you're doing is you're adding, this is in equilibrium, because you have some solid there. So it must be in equilibrium. You have some solid there, so now you're adding more barium ions. So you're doing a Le Chatelier thing. You're saying, I'm increasing the concentration of this. And if you increase the concentration of this barium, that will drive this equilibrium back towards the solid. That essentially is hurting you. It's not dissolving. It's making more solid. Same thing if you add H2SO4. That makes SO4 minus ions. Those are also a product. That hurts you and doesn't allow you to dissolve. So that makes the situation worse. The only option is to add more water. Adding more water lowers the concentration of both of them because you're just diluting them. So their concentrations go down, and then you can go in this direction. Reducing those, Le Chatelier says, go back towards the products and make more ions that would dissolve some of your salt. So that's the common ion effect. We just kind of talked through it. I think I'm going to do it with some numbers here. So the K, as I told you, for this one, very much greater than 1. All that dissolves and makes sulfate ions. So if you were to start out with X moles of barium and X moles of sulfate, and you add 0.1, you bring the solution to 0.1 molar H2SO4, that would increase the concentration of the sulfate by 0.1 molar. So that's a Le Chatelier's principal effect. You went from X and X to X and 0.1 plus X. You made a change, but you can still do the product. The new concentrations have to solve the equilibrium constant. So this concentration and this new concentration, the product of those two concentrations, barium and sulfate, still have to be KSP. It's still at equilibrium. Well, it's not at equilibrium immediately. It's going to go towards equilibrium. And you know this is 10 to the minus 10, so you say, under these conditions, what is this value of X? So you solve for X. You could do it with a calculator or something, but easy way to approximate it is you can say K is incredibly small. So if K is very small, then these numbers X were small. Before you added the 0.1 molar, those values X were small because K is small. These numbers are tiny. And we know they were 10 to the minus 5th, we said, if you just put some in there. So these numbers are something like 10 to the minus 5th. So 10 to the minus 5th plus 0.1 is just 0.1, right? It's, we can write it down. This one is 0.1 plus 0.00001, right? That's still pretty much just 0.1. So an easy way to solve it is just kind of just call that what it is. X is much smaller than 0.1, so just call it 0.1. And if you do that, then you can solve for X. The barium concentration is 10 to the minus 9. And that is what you expected. You said it would, if it started at 10 to the minus 5, you add some of this stuff, you expect it to go back this way. It does, the concentration goes way down to 10 to the minus 9. So you see what you expect to happen in some, the actual mathematical expression for K. I think I'm just gonna stop here because we'll have to do this on Monday. There's a demonstration involved with this next part, and it'll take more than 5 minutes. So we'll do that on Monday. Email Henry if there's a problem with the new final arrangement. We'll try to accommodate you, but there won't be very many accommodations we can make. We expect you to come take the final in person on Thursday.